Welcome to Algebra 2. Today we've got section 1.4, day 1. Section 1.4 is all about solving systems of linear equations, and today we're going to start off, hopefully this is a review section from Algebra 1, how to solve two-variable systems. All right, first of all, what is a system of equations, to refresh our memory a little bit? A system of linear equations is a combination of two or more known linear equations that are relating to variables. And really, it doesn't have to be linear equations. That's all we're going to work with for now. But any two equations that have two variables, we can set up in a system, and since they're dealing with two unknowns, we're able to find an intersection point between those two functions, and that often leads to really valuable information. When does our profit match, when does our cost of running our business match our revenue? That's our break-even point. That's when our business starts making money once we get past that intersection point. So really useful information can be found by solving systems. The solution is where the graphs, if we want to imagine these graphs of lines in this section today, where would they intersect? So the point would have an x and a y, or the solution for two of those variables could be the unit and the price of the unit if we were in a real-world situation, something like that. If we're setting up a system of equations, it is possible to have a system that contains more than one equation. More than two equations. If that were the case, just realize that if we're trying to deal with more than two variables, we better have more than two equations to make that system viable. So how have we learned to do this in the past? You can see this middle blurb that we've got here on screen. In the past, we've learned to either use graphing to find the intersection point. We learned the substitution method to solve algebraically, and also the elimination method to solve algebraically. That's what we're going to be reviewing today. And then the last bit, as I had kind of alluded to with our business analogy, this is really useful because it helps us find optimum values when there's more than one variable at work. All right, so there are three types of solutions when we're solving a system of equations in two variables, to a system of linear equations, I should say. The first type, there's exactly one solution. So we have the graphs of two lines, and they intersect at one point. Okay, so we get a solution x comma y. We have infinitely many solutions when the graphs are intersecting at infinitely many points. And how we note this, say we didn't have a graph to work with, we're solving by substitution or elimination. We would know that this happens when we get 0 equals 0 after all of our algebra has occurred. Okay, and then lastly, no solutions. This happens when we end up with all of our variables canceling out, and we end up with something like 0 equals a number, 0 equals 7, or two numbers that are not equal to each other after everything is simplified. Okay, so that doesn't have to be 7, that's just an example, but that's what we would see if there's no solutions. You can see from the graph, those lines are parallel. There is no point at which those two lines intersect. All right, so our first example, solve the system by graphing. We're going to pull on a little of the information from our refresher packet and earlier in this chapter. We want to graph these two lines as efficiently as possible, and you can see that the way they're given to us is not very easy to graph as it stands. So I'm going to arrange them into slope-intercept form. That's easiest for me to graph. For the first equation, I'm going to add y to both sides. That way, I've got y on one side of the equal sign equal to a positive x and a positive 1. So if I were to graph this, I would go up to the y-intercept at positive 1, and my slope, 1 in front of x, tells me rise 1, run 1. And I'll keep that pattern going to plot that line. And if I were working on paper, I would use a straight edge. Want as perfect of a line as possible. What if it intersects at a place where it's not on our grid lines? We want to be sure that we have a perfectly straight graph in order to interpret the results when we're solving graphically. For the second equation, I'm going to start by adding x to both sides. Then I have negative 2y equals x minus 8, and I divide both sides by negative 2. Finish solving for y. I find y equals x divided by negative 2. I'm going to call that negative 1/2 x. Negative 8 divided by negative 2 plus 4. I'll go up to my plus 4, count off my rise over run, sloping down to the right gradually, down 1, right 2. All right, now we've got the graph drawn, but we haven't solved it, right? We need an answer expressed. This is our solution point where those graphs intersect. So our solution is the point, the ordered pair, 2, 3. Not x equals 2, y equals 3, but the ordered pair solution. Easy enough, hopefully a refresher from last year. Example 2 here, we've got solve the system by substitution. Now, substitution is a good method to use. It's a very fast method to use if we have variables that have no coefficients, like that 1x and that 1y that we see underlined there that I just kind of pointed out. So to solve by substitution, I want to isolate one of the variables. So in this case, I'll add y to both sides. Then I find out that x is equal to y plus 5. And I'm going to hang on to that. That's going to be my substitution I'm going to make later. I'm just going to substitute that in to the other equation. That way I involve both of these linear equations in my solving process. Let's see what equation we get once that substitution is made. I now have negative 2x. I'm just copying that top problem. And then instead of minus y, oh, I'm sorry. It's not negative 2 times x anymore. I know that x is y plus 5. So I'm going to replace that x with y plus 5. And then finish off the equation. Minus y equals negative 4. You can see now I have an equation that just has y's in it. So I'm going to go through, and this will allow me to solve for y. If I distribute the negative 2, combine like terms, add 10 to both sides, and divide both sides by negative 3, I find that y equals negative 2. And again, I'm just going to hang on to this for now. It's not my solution. Even though it kind of feels like it, it's not my solution. I only found part of that intersection point, not the whole thing. All right, so I know that my answer is going to be something comma negative 2. I just need to find the x value. And thankfully, right up here, we have a nice little way of finding x. If I substitute in, now that I know y is negative 2, substitute in negative 2 into that little mini equation, I quickly find that x equals 3. So our solution is the point 3, negative 2. And if I wanted to check my work, all I need to do is plug in the 3 and the negative 2 for x and y, make sure it works in both equations up above. Usually that's pretty quick mental math. Okay. I'd like you to take a second and try the second system on your own. If you're feeling up to it, I'll check back in a couple seconds with my solution. All right, here we go. So for the first equation, that's where I notice I've got a 1x right there. So I'm going to subtract y from both sides, find out that x is equal to negative y minus 5. There's my substitution that's going to take place. I'm going to plug that in for x into the equation that I haven't used yet. I arrive at negative 2 times not x anymore. I'm substituting in negative y minus 5. Minus 2y equals 10. Let's distribute. Positive 2y, positive 10, negative 2y equals 10. If I combine like terms, oh, I get my y terms to cancel out. And I've got 10 equals 10. Subtract 10 from both sides, I get 0 equals 0. That's what we call infinitely many solutions. And the nice thing about that is, with infinitely many solutions, we get to that answer pretty quickly, and we're done. Right? There's nothing else we can really do with that. We've got the problem done, and you'll see it's much less writing than when we have to go back and find the other missing value. So we're in good shape. All right, example 3, solve the system by elimination. This involved us, if you remember from Algebra 1, what we had to do was get the system set up so that our x's, our y's, our equal signs, and our constants are all nice and lined up. And that way we can combine like terms. We may need to adjust here or there to make one of the variables eliminate. So when I combine them, I want them to cancel out. one of the variables, eliminate it. But let's just get started. Let's dive right into this first example here and kind of refresh our memory. So the proper way, or what I should say, the standard way to set these up is to have your x term, your y term equals your number. So I'm going to go ahead and set up my second equation that way by subtracting 12y from both sides. And now I'm going to copy the entire system down. Negative 5x minus 3y equals negative 13. I didn't need to change that top equation. But now I've got negative 20x minus 12y equals negative 40 for my second equation. You can see how everything lines up perfectly in order to combine like terms. Now, what we are allowed to do is we're allowed to either multiply or divide one or both equations in order to get those variables set up to eliminate. So I've got to make a decision. Which variable, the x's or the y's, does it look easier to eliminate? And I'm going to choose the x's for this one. It looks like they're very close to eliminating right now, or it wouldn't be a difficult adjustment. But instead of one of them saying negative 5, the other saying negative 20, I'd like for them to be like negative 5 and positive 5, negative 20 and positive 20. So I just need to think, how am I going to adjust to make that happen? And what I decide is that I'm going to multiply the top equation by negative 4. As long as I'm treating both sides of that equation equally, I'm not breaking any math rules, but in multiplying by negative 4, I should get that type of cancellation set up. Now, this is not the only route I could have taken. I could have also divided the bottom equation by negative 4, and that would have done the same thing. But let's see where we're at after we multiply in this negative 4. Now my top equation becomes positive 20x plus 12y equals positive, what's that going to be, 52? And my bottom equation, I didn't change anything about. Now I'm going to combine the like terms. If I combine the x's together, 20x and negative 20x, I get 0. If I combine the y's together, positive 12y and negative 12y, that's 0. 52 and negative 40 makes 12. So I end up with 0 equals 12, which we said was a no solutions situation. 0 equals a number. We can't really work with that. However, maybe I did get, one of the variables to cancel and the other one not to cancel. Then I would have something where I could solve for the variable that remained. And we could work our way back from there. All right, again, I'd like you to pause the video and try the next one on your own. I will check back in a couple seconds with my solution. All right, let's see what we can do here. Well, first, what I want to do is get it set up so my x's, y's, and numbers are in the appropriate order. So I've got a negative 6x and a positive 5y that are set equal to 10. And I didn't really have to move anything around like across the equal sign. I didn't have to add an x term to both sides or anything like that. I just kind of switched it around and put all the terms in order. Second equation, negative 24x, then a positive 18y equals 36. All right, which variable looks easiest to set up for elimination? I would probably choose the x's here, just because to get the 5 and 18 and the y's to eliminate, I'd have to do a lot more work. So what can I do? Well, if I want to turn this negative 6x into a positive 24x, I just need to multiply by negative 4. Oh, that's kind of funny. It's the same thing we had to do in the last one. It won't always be that way, but it happened this way in this lesson. So let's see what our equation looks like now, or our system of equations looks like. In the top, when I multiply in that negative 4, I get positive 24x minus 20y equals negative 40. And then the second equation I did not change. Now I'm all set up so that when I combine like terms, my x terms will cancel out. I will end up with negative 2y when I combine those like terms, and that equals negative 4. Oh, look at this nice little equation I quickly arrived at. I can easily solve for y now, divide both sides by negative 2, and find that y equals 2. And I'm just going to hang on to that. I now know that my solution is something, comma, 2. Let's find that something. The best way to do this, I say, is to always go back to the original. Which one of those original two equations looks easiest? We've already involved both of them. So what looks like the easiest place to plug in a y? I would choose the top equation. And if I plug that 2 in, I get 10 equals 5 times 2, that's 10, minus 6 times x. And let's solve that for x. I'm going to subtract 10 from both sides, divide both sides by -6, and I find that x equals 0. Now, 0 is totally acceptable when a variable equals 0. A lot of times students will find if they solved and find x equals 0, they'll say no solutions, but that's simply not true. A variable can equal 0. The point 0, 2 exists on our coordinate plane, so this one works out just fine. We have the solution point 0, 2. All right, and our final example, word problems. We said that this was a useful method in real life of answering when we have more than one unknown. So let's see a particular instance where that can be the case. The senior classes at High School A and High School B planned separate trips to the indoor climbing gym. The senior class at High School A rented and filled 2 vans and 14 buses with 590 students. High School B rented and filled 2 vans and 7 buses with 303 students. Each van and each bus carried the same number of students. How many students can a van carry? How about a bus? All right, well, the first objective when you're doing these types of problems is to figure out what you're trying to find. What is unknown that we want to know? In this case, it's how many students can fit in a van, how many students can fit in a bus. So I'm going to make a little note right away that B, one of my unknowns, is number of students per bus. And V equals the number of students per van. So now I have variables to work with. I've got things that I can solve for that will answer the question. That is a crucial first step when you're dealing with word problems of any type, really. Figure out what you're looking for. RTQ, I call it. Read the question. All right, now let's look at the situations. Because somewhere in here, since we have 2 unknowns, we're going to have 2 equations that relate those unknowns. Okay, and so here it's going to be the 2 separate trips. What's High School A doing? Well, they had 2 vans and 14 buses, and that totaled 590 students. High School B, they had 2 vans and 7 buses with 303 students. So just like that, we can turn the written sentences into math equations that say the same thing, but now we've got variables that we can solve for, and that's really, really useful. Now, at this point, you get to make the decision. Is substitution going to be easier, or will elimination be easier? I certainly don't want to graph those 2 lines when you see numbers like 590 and 303. That would be really difficult to graph accurately, really painstaking. It could be done, but it would be a really tedious task. I'm going to choose the elimination method just because we've got 2v in both of those equations. So if I multiply one of these equations, it doesn't matter which one, I'm just going to choose the top one, by -1, it will change that 2v into a -2v and set up elimination very nicely. So I'm just going to copy this revised first equation underneath. -2v minus 14b equals -590. And now I'm going to carry out elimination with these 2 equations after I've made that adjustment. All right, so if I set it up and eliminate, my v variable is completely wiped out. I find that -7b equals -287. And if I divide both sides by -7, I find that b equals 41. All right, and that's important. I'm going to hang on to that. I haven't finished answering the question yet. I now know this, but I don't know what v represents just yet. So I got to go back to my original 2 equations. Which one looks easiest to work with? I'm going to choose the second one, just because it has more manageable numbers. Obviously, we probably want to use a calculator to help us out with some of the arithmetic here, but I've got a better shot at using the second one without a calculator if it comes down to it. All right, so we know that B equals 41. Now that's telling me that 2 times V, I still don't know that, plus 7 times 41 is going to equal 303. 2V plus 287 equals 303. I subtract 287 from both sides. I find that 2V equals, oh, what's that going to be, 16? And if I divide both sides by 2, I find that V equals 8. All right, now I've found both variables. I need to be sure that I'm explaining what those numbers mean. All right, so to ultimately answer the question, 41 students per bus and 8 students per van. Now, whoever's reading this work knows when I found 41 and I found 8, exactly what those numbers mean in this situation. All right, so there you have it. That's our first day here in section 1.4. We've got a day 1 worksheet coming your way for an assignment. Be sure that you're checking your work. We didn't go through in detail how to check those solutions, but I did tell you how to check them. And we'll talk about in class ways that we can use calculators to help us with this as well. Most importantly, keep asking questions, keep advocating for yourself and getting quality practice out of the homework. There's a really, really meaningful topic of mathematics and something that you will keep using the rest of your high school careers and beyond probably. So that does it. Hope you've enjoyed this lesson.